All right. Let's jump into Unit 7. Unit 7 is going to kind of get shot out of a cannon here, so to speak. We're gonna rip through about 6 topics over the next 3 days.
How many topics are there in the unit?
13.
Okay.
Yeah, so we'll go through the early topics really fast, and then whoa, that's interesting.
Is it like on the full side?
Well, yeah, I mean normally it fills up the screen. Let's try this again. Sorry, people at home, we got technical difficulties. Take 2. Hopefully it goes back to normal. Anyway, so yeah, there we go. Yeah, I don't know what that was all about, but yeah, so we'll go through the early parts of Unit 7 really fast. There's a lot of it is review. You guys did this last year, and it should have been pre-pandemic according to my calculations. It's probably the very last unit you did before we ended up leaving last spring. So in theory, this is still maybe a little bit up there. Don't worry, I will start back at square one and we'll certainly build a foundation. So Unit 7 is all about equilibrium and reversible reactions and things like that. So we'll talk, we'll get through about 2.5 topics today. We'll finish 1 and 2 and we'll jump into topic 3. I cut it short just a little bit because again, it was a little, there's a lot, you know what I mean? Like I don't want to get too far in any one given day. So we'll probably stop with like 10-ish minutes left in the hour, just to kind of have a nice, clean stopping point for picking it back up tomorrow. But all right, so let's jump into it. We are talking about equilibrium. Many chemical and physical processes are reversible. Okay? For example, if I have an ice cube and I were to take that ice cube out of the freezer, and I can melt it, right? I can just put it in a cup and let it sit there for, I don't know, maybe 45 minutes, and it'll be all melted, turn into liquid water. I could then take that cup with my liquid melted ice cube in it, put it in the freezer, and refreeze it. Okay? Phase change, right? We're just melting and freezing something, and it's a phase change. Totally 100% reversible. Okay? Very obviously, you can totally refreeze water after it's melted, or vice versa. Right? Nothing special there. We also have other reversible examples. Bronsted-Lowry acid-base reactions are reversible. Do you remember what a Bronsted-Lowry acid-base reaction is? Bronsted-Lowry acids. Yeah.
It was the one with like the hydrogen donor and the hydrogen.
Yes. Yes. Yeah. Protons and hydrogen ions are the same thing, right? So Bronsted-Lowry acids donate hydrogen ions or protons, and Bronsted-Lowry bases accept hydrogen ions or protons. Now, those reactions are reversible, meaning if I have a Bronsted-Lowry acid that donates a hydrogen to a Bronsted-Lowry base, if I change the pH of that solution, I can actually force that Bronsted-Lowry reaction to go backwards in reverse of what it just did. Okay, totally possible. Was somebody asking a question or something? No, okay. There was some weird sound coming through. I don't know if somebody unmuted. But anyway, also redox reactions. We talk about redox just for a smidge in Unit 4, okay, at the tail end of Unit 4. But redox reactions are reversible. We have an oxidation half reaction, we have a reduction half reaction, and I can flip that whole process and turn my oxidation into reduction and my reduction into oxidation and just run that whole process backwards, okay? So long story short, as kind of an intro, a lot of things or a lot of chemical and physical processes can go both ways, okay? I can take a chemical reaction, push it in the forward direction, and then change the conditions of some way somehow and force it to go reverse and turn back into the reactants it originally was. Okay, very possible, very common. So when a chemical reaction is said to be reversible, what am I trying to say? What I'm trying to say is that both the forward and reverse reactions can happen. Okay, that's all I'm trying to say with that statement, right? A reversible reaction means that I can take reactants, turn them into products, but I can also take products and turn them back into reactants, okay? Both the forward direction and the reverse direction are possible, can happen, and do happen. Just wait a little bit, make sure everyone online is right. I can't see them, so they're probably just not right. They're good. I bet you they're right. So at some point in time, okay, depending upon the conditions again, right? Because if I mess with temperature, or if I mess with molarity, or if I mess with pressure, okay, that can have a huge effect on my chemical reaction. But anyway, so at some point in time, your forward or your reversible reaction, I should say, can reach equilibrium. Now, equilibrium means that I have a chemical reaction where the rate of the forward reaction is equal to the rate of the reverse reaction or the backwards reaction. Okay? So essentially, both processes are happening at the exact same time. The forward reaction is turning reactants into products. The reverse reaction is turning products into reactants. Both the forward reaction and the reverse reaction are happening at the exact same time. At some point, if the forward reaction and the reverse reaction are happening at the exact same rate, that is called equilibrium. What it means is that however fast I'm producing products, I am equally as fast producing reactants. Okay, that's called equilibrium. And that's what this entire unit is all about. A good chunk of this unit is conceptual, kind of like this stuff, right? Here's some definitions. Let's talk about the concept. Why does this happen? How do we describe what's happening? That kind of stuff. And then there's also a mathematical chunk of this unit. The math isn't too extensive, and it's pretty darn easy, actually. Like the math is all, like, if you've noticed, all the math in AP Chem is pretty straightforward, right? This isn't a math class. We're not doing anything crazy calculus stuff, but, you know, it's a lot of algebra, setting up equations, solving for an unknown. So the math should be pretty darn easy in this class. It's just, you know, understanding how we use it and how to make sense of it, I guess, is maybe the difficult stuff. Okay, so what's really important about equilibrium is that you understand that it is dynamic. Now, that word dynamic means that things are happening, all right? If I were in a chemical lab, like I am, I guess, if I were in a lab and I had an equilibrium reaction going on in a beaker, okay, when it reaches equilibrium, the molarity of the reactants and the molarity of the products are no longer changing. Because at equilibrium, again, however fast I'm producing products, I am equally as fast producing reactants. So in other words, at equilibrium, the molarities of my reactants and products are constant. So as an observer, it kind of feels like nothing's going on, right? If the molarities aren't changing at a certain point in time, it's like, oh, okay, it's done. Nothing's happening. But that is not the truth. Okay? Equilibrium is dynamic. What that means is, even though the molarity of my reactant and the molarity of my product are no longer changing, the forward reaction is still happening. The reverse reaction is still happening. That is what dynamic means. Equilibrium is a dynamic process. Both forward and reverse are still occurring. It's just that they're occurring at the exact same rate. So as a result, we see no change in molarity. Okay? Common misconception. Very, very common misconception that people think that when equilibrium is reached, nothing's happening. Not true. Not true whatsoever. When equilibrium is reached, both forward and reverse reaction are still going on. They're just happening at the same rate, so it looks like nothing's changing, and nothing really is changing, so to speak. Okay? True or false? When chemical equilibrium is reached, the concentrations or molarities of the reactants and products are equal. When equilibrium is reached, the molarities of the products and reactants are the same. What is equilibrium? When what is equal? The rate. Does the rate have anything to do with my molarity of reactant or product? I mean, it sort of does, but hold on. Like, what I mean by that is,
Isn't the rate of energy which transfers it does not have or does it? You're confusing me.
good.
They are reacting the same. Reacting.
Yeah. So this is false. This is false. Just because the rate of the forward reaction and the rate of the reverse reaction are the same, doesn't mean that the quantities on either side are the same. Okay? I could have completely different molarities on both sides of my equilibrium, or both sides of my reversible reaction. But equilibrium can still be reached. Even if the molarity on the product side is 4 and the molarity on the reactant side is 0.1, I can still be at equilibrium as long as the forward reaction and the reverse reaction are have equal rates. Okay, so it's not the molarity that is equal, it is the rate that is equal. Be very, 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 very careful with that. Okay, it is the rate that is equal, not the molarity. All right, here's a hypothetical. Oh, not yet, I'm sorry. So when a chemical reaction has reached equilibrium, again, the forward and reverse reaction are occurring at the same rate. I've said that like, I don't know, a solid 13 times at this point in the day. Okay, and I'll keep on saying it because it's really important, and you got to make sure you understand that. So if you get sick of me saying that, well, good. That means that maybe it's sunk in finally. All right, so here's a data table. I have a hypothetical reaction. I've got X plus Y giving us XY. Okay, this is not real stuff, obviously, but I have a data table down below with time and the molarities of my reactant X and the molarity of my product XY. As time goes on, okay, and 15 minutes, 30 minutes, 45 minutes, so on and so forth, keep on going forward. As time goes forward, the molarities of my reactants and products are changing, okay, until a certain point in time, the molarities kind of stop changing. The question here is, based upon this data, at approximately what time is equilibrium established for this reaction? Okay, when is equilibrium reached based on the data here? Yeah, somewhere between 90 and 105, right? I don't know where exactly in that spot because I don't have enough data points to find it. But certainly at 105 onward, we are at equilibrium. How do I know I'm at equilibrium? The molarities are no longer changing. What that's trying to imply is that, again, however fast I'm making the product XY, I am equally as fast producing the reactant X. Again, it didn't stop, okay? The molarities are unchanged after 105 minutes, but things are still happening. It's dynamic. Reactions are still taking place. It's just that the rates are equal, so the molarities are unchanged after that point in time. So when is this established? Okay, it was established between 90 and 105, right? But 105 minutes onward, equilibrium has been reached or established, or however you want to say that. Okay, that's one way of kind of looking at this, right? We can look at a data table based off of molarity, based off of time. Okay, at what point is equilibrium reached? Well, equilibrium is reached when these molarities are no longer changing. Because when molarities are no longer changing, rates are equal. We can use a graph and do the exact same thing. Here's a graph. On the y-axis, we have molarity. On the x-axis, we have time. And we can monitor the molarity over the course of time. Okay, I know that's, maybe that phrase gives you like PTSD from the kinetics lab or kinetics unit. Okay, molarity changes over the course of time. Well, don't worry, we're not diving back into kinetics. Don't worry, we're not going all the way back there, but we'll just talk about it just a smidge. Okay. As time progresses, molarities are changing. This white little dashed line here is going to be my reactant, N2O4. This black one with the little circles is going to be my product, NO2. At the very beginning, at time 0, I had a whole bunch of reactant and 0 product. And then the reaction starts taking place, right? And time progresses and time progresses and time progresses. At what time, based upon the graph, does this reaction reach equilibrium?
60 minutes.
Or seconds, not minutes.
60 seconds.
I agree.
Yeah.
Okay. At about 60 seconds, give or take, maybe a smidge more, right? It looks like we're not quite there, but yeah, pretty close. So right at 60 or a little after 60 seconds, you'll notice what happens to the molarities. They level off. They stop changing. Again, what is that trying to imply? It's trying to imply that the rate of production of the product and the rate of production of the reactant are the exact same. As fast as I'm producing this one, I am equally as fast producing this one, so their molarities go unchanged. That is equilibrium. Be very careful. Equilibrium is not this, right? Equilibrium is not when the two molarities are the same. That has nothing to do with anything. Okay, it looks nice, I guess. Hey, look, they're both a molarity of like 6.5. Okay, great. But that is not equilibrium. Equilibrium is when the rates are equal, not when the molarities are equal. This little graph will most likely show up on the AP test. And then they will say, at which point is equilibrium reached? And then they'll have this as one of the options. Oh, it sure could be simple. It's nice and simple right now after I've explained it.
Yeah, no, after you explain it, yeah.
But 2 months from now when you're taking that test, or 3 months from now when you're taking that test, and you look at that problem, you're going to be like, huh, that looks like a pretty good spot.
It's only 2 minutes away.
Yeah.
That's
Ah,
Yeah.
the ACT is like in like 2 weeks.
Is it really?
That much time.
Huh, no way.
Anyway, sorry for the rapey. Yeah. I should totally talk about that tomorrow. I should totally talk about that tomorrow. I'll do that. Anyway, so yes, it's not that point, right? It's not when the molarities are equal. It's when those molarities stop changing. Because when the molarities stop changing, that's when the rates are equal. So when is this? Approximately 60 seconds. Ish, right? Now, how do we know? We know because the molarity of N2O4 and the molarity of NO2 are no longer changing. This implies that the rate of the forward and reverse reactions are equal. Kind of a long-winded explanation. I left it up from last hour just to make sure I said it the same way. Okay, please write that down. But we know that that's equilibrium because the molarities are unchanged, implying that the rates are equal. So again, I've only said it like, you know, a solid like 16 times at this point. But equilibrium is equal rates, not equal molarity. Got it. Okay, good. Here's another graph showing the exact same information in a different way. This graph has rate versus time. The red line is your reverse reaction, or from products to reactants, right to left. The yellow line or orange line is your forward reaction from reactants to products. And if you're looking at your packet, the bottom one is gray and the top one is gray. Or yeah, more kind of blackish, grayish. At least one's dashed and one is solid. That's nice. But yes, you get nothing but black and white paper. Said marker. In this one, though, we have rate versus time. So the rate of the forward reaction at the very beginning is really high, right? Because at the beginning, I don't have any products yet. So it goes forward way faster than it would go backwards, because it can't go backwards if there's nothing to make it go backwards, right? I have to go forward first. So the forward reaction is going faster than the reverse reaction. But as we produce more of the products, the reverse reaction starts to gain speed, so to speak, or it picks up its rate. It's going a little bit faster. And at some point in time, the rate of the forward and the rate of the reverse end up being the exact same. Now, this is rate. Equilibrium is when rate is equal. So when does equilibrium occur? When they become equal. This is a different graph showing different info than the previous one. The previous one was molarity versus time. This is rate versus time. If it's rate versus time, we do want them to intersect because that is equilibrium. If the rate of the forward reaction is greater than the rate of the reverse reaction, what's going to happen to the concentration of the products over the course of time? If the forward reaction is going faster than the reverse reaction, what's going to happen to the concentration of the products? They will what? Absolutely. Makes perfect sense, right? The forward reaction is going faster, meaning I am producing products faster than I am producing reactants. Therefore, if the forward reaction is faster than the reverse reaction, my product's molarity will go up. For example, let's go back to that data table really, really quickly. If I'm at 60 minutes in this data table, we have not reached equilibrium just yet. The rate of the forward reaction producing XY, the product, is greater than the reaction of the reverse reaction producing X. So if you look at 60 minutes onward, the molarity of the product goes up because the forward reaction is currently going faster than the reverse reaction at that point in time. Now, once we get to 105 and beyond, the rates are equal, so the molarities go unchanged, right? But prior to that, the forward reaction must be going faster because the products are still increasing in their molarity. Okay, let's flip the script. If the rate of the reverse reaction is greater than the rate of the forward reaction, what's going to happen to the product's molarity over time? Now the backwards reaction is going faster than the forwards reaction. What happens to the molarity of the product? Yes. Okay. It's going to go down, right? Now, I'm using my products to make more reactants faster than I am using reactants to make more product. As a result, the molarity of my products must be decreasing over the course of time. Make sense? Pretty straightforward, I hope. Questions so far?
Reactions
Yes. Yeah, so that's a good question. The question was, is if a chemical reaction reaches equilibrium, can equilibrium be broken, or can it shift beyond that? Yeah. Now, in order for it to happen, we got to do something, right? But if you change the conditions, equilibrium will be broken. No, it won't just do it on its own. It doesn't randomly happen. It happens because of like a stress or an outside influence causes it to break and then shift again. Okay. So if I change the temperature, for example, that would break an equilibrium. All right. Last slide of 7.2, then we'll jump into 7.3. So equilibrium is often monitored by using molarities or concentrations, but it doesn't have to be. Okay? It doesn't have to be. If you have a reaction that is nothing but gas reactants, gas products, you can also use partial pressures. Okay? Partial pressures is the pressure, or a partial pressure is the pressure of an individual gas in a gas mixture. Okay, so if I have like a little container, and my container has oxygen, and it has nitrogen, and it has helium. Okay, it's a mixture of gases. Each of those gases individually has a partial pressure. There's a partial pressure of nitrogen, there's a partial pressure of oxygen, there's a partial pressure of the helium. If I add all those up, I get the total pressure. But we can use partial pressures to describe equilibrium through gases. If there's a reaction with just gases and nothing else, instead of using molarity, we can use partial pressures. All of the concepts are the exact same. In other words, the rate of the forward reaction still needs to equal the rate of the reverse reaction when we're using partial pressures. So all of the concepts are the exact same. It's just that instead of molarity, we use partial pressure. We have two equations in your formula packet dealing with partial pressures. We used these once before. It's been a while. Okay. If you go to the second page of formulas, the top section is called gases, liquids, and solutions. Equation 2 and equation 3 in that section are the partial pressure equations. The partial pressure of any gas, gas A, will equal the total pressure multiplied by the mole ratio or the mole fraction. Okay. For example, I have my mixture of oxygen and nitrogen and helium. Okay. Let's say I have a grand total pressure of 10 atmospheres. And I have 4 moles of oxygen, and there's 10 moles total. Okay. Pressure is 10 atmospheres. I have 4 moles of oxygen divided by 10 moles total for my mole ratio or my mole fraction. And my partial pressure of oxygen will then be 4 atmospheres, right? 4/10 of the total. And if the total is 10, then the partial pressure would be 4. So it's pretty easy math. The other one is, I already said this, the total pressure is all of these partial pressures added up. So if I have 3 gases mixed together, I will add the partial pressures of each of them individually to get the total. Just add them on up and you're good to go. So when partial pressures are used instead of molarities to monitor a reversible reaction, the core concepts are literally the exact same. Equilibrium is established when the rates are equal. Will the partial pressures of reactant gases and product gases be the same at equilibrium? Will the partial pressures of reactants and products equal one another at equilibrium? When the chemical equilibrium is reached, the concentration of the reactants and products are equal. True or false? False. When chemical equilibrium is reached, the partial pressures of the reactants and products are equal. False. Same exact concept. We're just replacing molarity with partial pressure. So again, it's not that the partial pressures are the same on both sides. It's that the rate is the same forward and reverse. But the partial pressures of the gases could be completely different on either side. The molarities of the reactants and products could be completely different on either side. Okay? Same concept, just replacing molarity with partial pressure. All right. Cool. 3.2 done.
1.2.
Yeah, it's 3.2.
3.2 Lisa.
That's been done for a while. 7.2. Yeah, done. Nice. At this rate, we'll test on Thursday. And we are not testing on Thursday. Sorry. Not going to happen. Could we? No. Well, I mean, I could, but I would only be able to teach you a little bit of the unit. Yep.
Please not get through all of it.
Not sufficiently. I could.
You have, like, the entire school.
Then I could.
No, I don't want that. I'm sorry.
That'd be fun.
That would not. I would probably.
It's like binge watching
I
Chem.
would probably fall asleep.
It'd be like
Me too.
watching a really weird thing.
For 7 hours. Are you saying I'm weird?
Yeah.
Try and listen, and all of a sudden my mind.
Good assessment. All right, let's switch over to 7374. If you're still with me online, thank you. I appreciate your attention. Let me switch my presentation. All right, I will not get too far into this, and like I said, I will stop early. So give me another, I don't know, 10-ish minutes of your attention, and I'll cut it a smidge short. Okay. 7.3 and 7.4 are going to introduce the math of equilibrium. Okay, and it's not bad. The math in this class in general just isn't bad, like I said earlier, right? It's algebra stuff every single time, so we'll be good to go. 7.3 is on the reaction quotient and the equilibrium constant. This is like a mathematical setup to describe the equilibrium. And then in 7.4, we'll actually start doing some math with solving this stuff and setting it up and plugging in numbers and all that good stuff. So here is the generic setup. When a chemical reaction reaches equilibrium, there's a value that we can calculate to represent the equilibrium. This is called the equilibrium constant, and it's given the symbol capital K, uppercase K. This is a reaction. The lowercase letters are coefficients. Okay. The little lowercase letters are coefficients, like numbers, right? You got 2 of those, you got 4 of those, you got 6 of them, you got 8 of those, whatever. Okay? They're coefficients. They're the numbers before the actual chemical. So the capital letters A, B, C, and D, these are all like formulas, right? H2O and CO2 or whatever. Okay? Chemical stuff. This is the mathematical setup of the equilibrium constant. Capital K is the equilibrium constant. It is often followed by a subscript. We will literally talk about like 7 different equilibrium constants. So the subscript will change a lot. Okay? And it means different things in different contexts. But if it's capital K, it's always an equilibrium constant. So there is literally a Ka, a Kb, a Kc, Kp, Ksp, Kw. There's all sorts of Ks because the letters mean different things. So it's not specifically like sequential. Ka is for an acid, Kb is for a base, Kp is for pressure, Ksp is for like solubility, Kw is for water.
Sounds a lot of fun, and I'm looking forward to it.
Yay.
Me too. Excellent.
Let's go.
Kc. Kc is for concentration. So this is a generic. But be on the lookout. There's a lot of subscripts with K. Again, same concept. It's still an equilibrium constant, just using a different context of what reaction we're looking at. Okay? So the math is set up always the same, regardless of the subscript of your K value. It's set up like this. You have your products, the molarities of your products raised to the power of their coefficient. My product is capital C. I have the molarity of that raised to the power of its coefficient. Maybe it's a 2, maybe it's a 3, maybe it's a 1. Okay. I then have my other product. I multiply these together. One product, two product, they are multiplied, both raised to their coefficients, divided by the reactants. A times B raised to their coefficients, multiplied together. It's always products over reactants. Does that ring a bell from last year? No?
Yeah.
Fair enough. It's not bad.
Oh, wait. Yeah. Keep going.
It should hopefully come back a little bit.
At some point.
I'm starting to remember.
We'll put real chemicals in here in the next slide. That'll help. Okay. So essentially, we just plug in the values of molarities for both reactants and products, and then we just raise those molarities to the power of the coefficient, whatever that might be. Again, the little A, B, C, and D are all numbers, right? That's like balancing a chemical equation. 1s and 2s and 4s, whatever. Okay. There are certain things that are included in this expression, and there are certain things that are excluded from this expression. The chemicals that are gases and aqueous are included in the expression. Gases and aqueous things go in an equilibrium constant expression. Pure solids and pure liquids are not. Good, that's good. So if you have gas reactants, gas products, aqueous reactants, aqueous products, every single one of those gets included in our setup. But if you have a pure solid or a pure liquid on either side, those do not get included. Now, here's why, because it's always like, well, that's kind of curious. Why? Pure solids and pure liquids, their molarities are constant. In other words, the concentration of a pure liquid or a pure solid is literally the exact same, regardless of how much there is. So they don't mathematically change anything in the expression. Gases and aqueous substances, their molarities can change, or their concentrations can change. So they get included because they can affect the equilibrium constant. But solids and liquids do not have a difference in molarity, regardless of how much there is. So they're not included. So aqueous gas, you put it in the expression. Solid liquid, you don't. You just ignore it. We literally ignore it and don't include it. All right, here's a real example. Let's set up the equilibrium constant expression for this reaction. K, and if you want to put a subscript C, you can. That's just trying to say, again, it means concentration. So this is an equilibrium constant expression using molarities. That's all that's trying to say. Most of the time that actually gets dropped. Most of the times you'll literally just see K all by itself, because it's kind of redundant to put the C, because again, we're using molarities almost always anyway. But I have K, capital K will equal my products divided by my reactants. My products raised to the power of their coefficient, multiplied together, divided by my reactants raised to the power of their coefficient, multiplied together. So I have the molarity of NO2 to the fourth power, multiplied by the molarity of H2O to the sixth power. They're both gas, so they get included. If this water were liquid, I would not include it. That would be an issue. I would have to literally get rid of that entire term. But it's a gas, so it must be in there. I divide my products by my reactants. My reactants are NH3 raised to the 4th power, and O2 raised to the 7th power. Again, please be a little careful. These are multiplied. This is not addition on the top or on the bottom. This is multiplication. Okay, we do multiply it. The molarity of NO2 to the 4th power multiplied by the molarity of H2O to the 6th power divided by the whole darn thing. Ammonia molarity to the 4th power multiplied by oxygen to the 7th power. Okay, so let's try one. We'll do one of these and do a smidge of math, and then we'll call it a day right there, and we'll pick this up tomorrow. Sound good? Here's our reaction. We have N2 plus 3H2 producing 2 NH3. First things first, let's set up the expression, and then let's plug in the numbers after the fact. My expression will look like this. K equals products over reactants. I have ammonia as a product, NH3. The coefficient was 2, so I square it. My reactants are N2, which is a coefficient of 1, so I just leave it as it is. If you want to write in a 1 for the exponent, you totally can, but obviously it's redundant. And H2 raised to the power of 3, because it has a coefficient of 3. There's the setup. Now I just plug in what I know. They have given us molarities. Now, what's really, really important is that these molarities are at equilibrium. If I just give you random molarities of random chemicals that are not at equilibrium, you can't plug them in to an equilibrium constant expression, because equilibrium constant is for, you know, equilibrium. That make sense? So if I just give you random molarities, you can't just automatically plug them in. They must be at equilibrium. And the molarities they gave us here are at equilibrium, so we're good to go. Kc equals, all right, NH3. What's the molarity of NH3? 3.1 times 10 to the negative 2. And that whole thing gets squared, divided by the molarity of N2, 8.5 times 10 to the negative 1, multiplied by the molarity of H2, which is 3.1 times 10 to the negative 3 cubed. There's my setup. Now, let's plug all that in. And our value of the equilibrium constant should be something. It really should be 2 sig figs, but with 3 sig figs, what do we get? Yes. This is our value of the equilibrium constant for this reaction under these conditions. Now, if you can't get your calculator to spit out that number, you got to enter it in a different way. Okay? Here's my recommendation. When I punch this in my calculator, here's what I do. I take 3.1 times 10 to the negative 2 squared, enter. Divided by 8.5 times 10 to the negative 1, enter. Divided by 3.1 times 10 to the negative 3 cubed, enter. I do it piece by piece by piece. It makes life easier. I feel like your calculator doesn't screw it up when you do it that way. Now, you do have to be a little careful as well. Please make sure that when you square things, you cube things, you take things to any power, right? Make sure that you're only taking that one piece to that power. You don't want to cube the whole answer, right? I just want to cube the 3.1 times 10 to the negative 3 part. So either way, make sure you can do this in your calculator. We'll pick this up tomorrow right here. For those of you at home, have a lovely day. If you have not taken the Unit 6 test, please find a chunk of time to take the Unit 6 test. About a smidge over half of you have done that already, but there is still a good 20 some of you who have not. So please, please, please take the Unit 6 test. I know last Thursday got thrown into a tailspin or whatever you want to call it. It was a weird day, so I do apologize for that, but sometime soon, hopefully take your Unit 6 test.